Hi there, this video is going to walk through how to obtain the eigenfunctions of a rigid rotor. And these eigenfunctions are also known by a special name called the spherical harmonics. So just remember that when we're talking about the spherical harmonics, they're just like any other wave function that we've worked with our other systems, except they just get this special notation of a capital Y, okay, rather than our psi that we've been using for our other wave function notations. Okay, so remember we are in spherical harmonics now, so our wave functions are going to end up being functions of theta and phi for this situation. And just like all of our other situations where we want to obtain eigenfunctions, we need to first start by solving our Schrodinger equation. So, very basic Schrodinger equation for the rigid rotor, right? So, essentially our H psi equals E psi, except that instead of psi, again, we're using our spherical harmonic notation, Y of theta and phi. Okay, so here we can plug in our value that we've obtained for the Hamiltonian. Okay, so here it is. This is our Hamiltonian for our spherical coordinates. Okay, so again, remember our model is in our spherical coordinates, and we have just the kinetic energy contributing here. So remember, we have no potential energy for our Hamiltonian for the rigid rotor, okay, according to our model assumptions. So this lovely mess right here is our Hamiltonian in the spherical coordinates, okay, and then we have our wave function still there, and then we get our E, Y on the other end. Okay, and then remember we still have our moment of inertia popping in there, so all of those things that we have already talked about in terms of our Hamiltonian. Okay, so now we want to work through solving this equation. Okay, so we're just going to take a couple of steps to try to simplify things for ourselves. So the first is going to be to multiply by sine squared theta. Okay, and then we're going to plug in also beta equals 2ie over h bar squared. So we're just going to put all of our constants that we have there in this beta term. Okay, so once we do that, we'll end up with a little bit of a modified version of this equation. And that's beta sine squared theta y. And everything equals 0. So we've just modified our expression up here. We've put all of our constants into this beta term, multiplied by sine squared theta, and just rearranged everything so that we get everything on the left-hand side of our equation, okay? And then we end up with this form of our Schrodinger equation. Okay, so now we need to solve this partial differential equation, and wouldn't you know, we are going to use our favorite method of solving partial differential equations, which is our separation of variables method. Okay, so this should sound familiar from what we've done earlier on in the semester. Okay, so it's going to be the same approach that we used when we solved the wave equation, that we ended up with when we did the particle in a box. Okay, so the approach here is going to be very similar. Okay, so if you remember with our separation of variables method, we make a substitution into our equation. So we are going to say that our wave function y of theta and phi can be broken up into two independent functions, one as a function of theta, one as a function of phi. Okay, so we've got big phi of little phi, big theta of little theta and big phi of little phi. So this is very similar to how when we did the wave equation, we had the big x of x and the big y of y as our separation expression. Okay, so then we sub this expression into our previous partial differential equation, and then we'll divide by theta of theta and phi of phi. Okay, so once that is done, we end up with this expression here. Okay, I try to be clear on my capital thetas and my little thetas. So I'll just modify that. So sometimes I go into the shorthand of just putting in the main function, but we know that they are functions of theta and phi. So here, this is a capital theta of little theta and another capital theta of little theta here. Big phi of little phi, big phi of little phi. Okay, all the other ones, these are all going to be your lowercase variables. Okay, so since we know that all of these terms sum up to equal 0, we can just start to group them. So let's take all of our theta terms into one group, and then we have all of our phi terms in that last group. Okay, so because we know that this whole expression equals 0, we can say that this group of terms is equal to a constant. And then that means that this group must be equal to the negative of that constant. Right? So constant minus constant equals 0. Okay? And we are going to give that constant a label. We're going to call that label m squared. Okay, so over here we would have negative m squared. Okay, and we're able to do that, we're able to do all of this process because we know that theta and phi are independent coordinates, okay? And then the other thing that we want to be careful of is we want to make sure that we do not confuse m with mass, okay? M is not equal to mass here. Okay, this is actually going to become our magnetic quantum number when we start diving into the hydrogen atom. So just keep that clear in your head when you're working with these labels. Okay, so M here is going to be our constant. Later we're going to see that become one of our quantum numbers that we know for the hydrogen atom. Okay, so that is just an overview of how we set up the separation of variables to solve the Schrodinger equation for the rigid rotor, and we'll look at the explicit wave functions, so the phi component and the theta component of these wave functions, and how to obtain those in some subsequent videos. Thanks.